So we'll go for some problems on the fatigue loads. Okay. So design for fatigue strength. So we made a discussion that we are going to get mainly three types of stresses. That is what this one is what a fluctuating stress. Fluctuating stress. Okay. So this is what repeated stress. Repeated stress. And this one is completely reversed stress. Completely reversed stress. Okay. So in fluctuating stress, what happens is you are going to get the magnitudes on one direction. Okay. So they have gone for strain. So now you will get a tensile here. You will get a tensile. Okay. So now this is what a sigma max. So now this is what a sigma A, and this is what a sigma minimum. This is what sigma amplitude. Okay. So here there is a sigma amplitude. Okay. So this is what the variation of value. Okay. This is what variation of value. Okay. So here this is what repeated stress. In repeated stress, so minimum sigma minimum is 0 here. Sigma minimum is 0, and you have some value of sigma max. Okay. But in case of completely reverse stresses, so sigma max is equal to, okay, so minus sigma minimum. Okay. So one side you will get a compressive, that is what a minimum stress, on one side you will get a tensile stress. So we have a lot of theories here to find out the the calculation of the parameters, either stresses or either dimensions. You have three theories here. One is Soderberg, another one is Gerber, another one is Goodman, and next one is a modified Goodman line. Okay. So now we are going to have the problem on Soderberg as well as Goodman relationship. Okay. We'll solve some problems on Soderberg as well as Goodman relationship. So now Soderberg stands for ductile materials. Soderberg stands for ductile materials. And Goodman stands for brittle material. Goodman stands for brittle materials, right? So let us see. So we have a problem here. SI 1045 steel rod is subjected to a tensile load that varies from 60 to 120 kilonewton. Okay. So material had ultimate stress of 586 megapascal. So yield stress of 309.9 megapascal and entrance stress of 290 megapascal. Find the diameter of the rod. So taking factor of safety as tau. Okay. So now let us note down given data here. So F minimum they have given, it is how much, 60 kilonewton. Okay. So F max is 120 kilonewton. Okay. So if you draw the diagram, it is just a steel rod. Okay. It's the steel rod. You need to find out its diameter. Okay. So which is subjected to two type of loads here. One is F minimum, another one is F max. Okay. One is F minimum, another one is F max. So you can calculate the values in terms of stresses in terms of diameter itself. Otherwise, you calculate values in terms of loads. Then you can substitute in final equation. So now let us go for the calculation of stresses. So first we will calculate the minimum stress. Okay. We calculate first minimum stress. Minimum stress, let us make it as a sigma minimum. This is what F minimum by area. So I will go for 60 into 10 to the power of 3 as it is. I will go for area as it is. Okay. This is what minimum stress. So next we will go for maximum stress. sigma max equal to F max by A. This is how much? 120 power of 3 divided by A. So as you know, you need to find out the amplitude stress as well as mean stress here. Amplitude stress as well as mean stress. So let us first find out the mean stress. Mean stress or average stress. So now sigma m equal to sigma max plus sigma minimum divided by 2. Divided by 2. Okay. So now this is how much? Both values are positive. 16 to 10 to the power of 3 plus 120 10 to the power of 3 divided by A divided by A. So how much you will get? You are going to get 19 to 10 to the power of 3 divided by A. This is what sigma m. So now we will go for amplitude stress. Or alternating stress. I'll see variable stress. Variable stress. So now sigma AMP, okay, AMP equal to sigma max minus sigma minimum divided by 2. So now sigma max is 120 into 10 to the power of 3 divided by A minus sigma minimum is 60 into 10 to the power of 3 divided by A. So you are going to get, so it is whole divided by 2, sorry. It's also whole divided by 2. So you are going to get 30 into 10 to the power of 3 divided by A. So let us note on this is the third equation. This says, okay, this is third equation, this is fourth equation. So now they have given all values. Factor of safety is given, yield stress is given, ultimate stress is given, as well as entrance stress is also given. So now you need to find out value of A. Once you got the value of A, you can calculate diameter. You can calculate diameter. Okay. So now let us refer design data and book. So to calculate this mean stress or variable stress. Okay. So you refer data and book. You have equation number 2.16a. Okay. So for this one you refer design data and book, equation number 2.16b. Right. Next. So let us go for the calculation in accordance with Goodman's relation. Okay. In accordance with Goodman relation. So in this case, as they have specified, it is the axial load. As there is the axial load. Okay. So you need to consider some parameters here. That is what size correction factor, surface correction factor, as well as load factor. Okay. If they are not specified, let us assume. So now in problem, have they specified? They have not specified nothing. Okay. So now let us assume. Assuming load factor. Okay. So as it is a reversed axial, you can assume from 1.7 to 1. So let us go for A equal to 1. Okay. A equal to 1. Next. So size correction factor, you have equations, you need to refer some equations and you need to substitute values. Okay. So now what I will do, I will go for some just 0.85. Okay. And for C, I will go for 0.85. here you can assume, or you can consider B equal to 1, C equal to 1 as they are not specified, actually you need to consider some value. Okay, if they are not specified, you assume. ಅವರು ಕೊಟ್ಟಿಲ್ಲ ಅಂದರೆ ಅಸ್ಯೂಮ್ ಮಾಡ್ಕೊಳ್ರಿ. ಏನು ಅಸ್ಯೂಮ್ ಮಾಡ್ಕೊಳ್ರಿ? ಬಿ ಈಕ್ವಲ್ ಟು 0.85 ಅಸ್ಯೂಮ್ ಮಾಡ್ಕೊಳ್ರಿ, ಸಿ ಈಕ್ವಲ್ ಟು 0.85 ಅಸ್ಯೂಮ್ ಮಾಡ್ಕೊಳ್ರಿ. ಸೊ ದ ವ್ಯಾಲ್ಯೂ ರೇಂಜಸ್ ಆರ್ ಗಿವನ್. ಓಕೆ, ಅಥವಾ ಬಿ ಈಕ್ವಲ್ ಟು 1, ಸಿ ಈಕ್ವಲ್ ಟು 1. ಲೆಟ್ ಅಸ್ ಅಸ್ಯೂಮ್ ಆ್ಯಂಡ್ ರೈಟ್. ಓಕೆ, ಸೊ ಅಸ್ಯೂಮ್ ಮಾಡಲಾರ್ದೆ ನೀವು ಬರೀಲಿಕ್ಕೆ ಸಾಲ್ವ್ ಮಾಡಲಿಕ್ಕೆ ಹೋಗಬಾರ್ದು. ಸೊ ಯು ಕ್ಯಾನ್ ಹ್ಯಾವ್ ದೀಸ್ ಡಾಟಾಸ್ ಫ್ರಮ್ ಡಿಸೈನ್ ಡಾಟಾ ಆ್ಯಂಡ್ ಬುಕ್ in page number 25. In page number 25. Next, so now as they have given both the values, that is what ultimate stress as well as yield stress as well as endurance stress. Okay? You can refer equation number 2.21a. Okay? So let us go for the equation. That is what so now we will calculate diameter of rod based on Goodman relationship. Okay, so refer design data and book. Okay, so equation number 2.21a. Okay, 2.21a for ductile materials. Okay, for ductile materials, right? Now in this case, as it is a simple bar, you can assume KTF, that is what fatigue stress concentration factor equal to 1, A equal to 1, B equal to 0.85, C equal to 0.85. So now let us substitute. So what is the equation? Equation 1 by n equal to KTF into sigma A, okay, divided by ABC into sigma En plus sigma m divided by sigma u. Now in this case, so sigma A you have calculated, it is 30 into 10 to the power of 3 divided by A. Okay, sigma m already have calculated. This is how much? 90 into 10 to the power of 3 divided by A. Okay. Right, now sigma u is given from data and book. You just select sigma y. Okay, so sigma u is given. Okay, sigma u is given. So now let us substitute. KTF1, okay, sigma A is 30 into 10 to the power of 3, okay, divided by A is 1, okay, B is 0.85, C is 0.85, okay, sigma En. Okay, so sigma En, you just check it from data and book. So now we are going to get a term here because of this one. Alternating stress, due to alternating stress you will get a. A means area, not a constant. Okay, now sigma En is 290. Okay, sigma En is 290. Okay, that is sigma m. So sigma m is 90 into 10 to the power of 3 divided by A. Now ultimate stress is 586 megapascal. Okay, so factor of safety is N is given, N is 2. Okay, So now solve this equation. So solve this equation, okay. You will get value of A. You will get value of A. You can say write AD. Don't get confused. You can just write AD. Otherwise, you will get a confusion. Area. You can write AS. Okay. You can write AS. Otherwise, you substitute A equal to what? Pi by 4 d square. Okay. You can substitute area. Okay. So let us find out value of A. Then you obtain diameter of shaft. Okay. So diameter of shaft you just calculate. Okay. D. Right. Similarly, you calculate based on Soderberg relation. So for Soderberg relations, you refer equation number 2.21c. Now diameter of rod based on Soderberg relation. Okay. Soderberg relationship. So refer design data handbook. Notify equation number 2.21 C. Okay. 2.21 C. Right. So it's the same equation. Again, equation is KTF into sigma A divided by ABC into sigma En plus sigma M divided by sigma Yp. This is equal to 1 by N. Okay? 1 by N. Substitute again all parameters, find out value of A, then you find out diameter. Okay? You find out area A, then you calculate diameter. Right? Next, so one more problem. A grooved shaft of diameter D, okay, so capital D, has a semicircular groove of radius 0.1 d, is made of steel having torsional yield stress of 300 megapascal and a torsional endurance stress of 210 megapascal. Okay, the size and surface factors are 0.85 and 0.87 respectively. The notch sensitivity index factor is 0.95. Okay. The shaft is to sustain a twisting moment that fluctuates between plus 900 Newton meter to minus 300 Newton meter. Find the diameter of the shaft taking factor of safety as 3. So now let us draw the diagram here. Okay. Draw the diagram. So given data, so it is a shaft, which has a diameter capital D, okay, so which has a groove of radius 0.1 r equal to 0.1 d. Let us check it. Okay, 0.1, radius is 0.1. So next they have given torsional yield stress. Torsional yield stress is how much? 300 megapascal. Okay. Then endurance stress 210. Endurance stress at 210 megapascal. Now value of B and C is given. Okay. So value of B is 0.85, value of C is 0.87. So now sensitivity index Q is 0.95. Okay. Right. Now factor of safety FOS equal to N equal to 3 is given. okay, and T max is 900 Newton meter and T minimum is minus 300 Newton meter. T minimum is minus 300 Newton meter. Okay. So, we need to find out what is the diameter here. Okay. Diameter of the shaft which fluctuates between the torques T minimum to T maximum, right? Clear. So, now let us go for solution. Let us go for solution. Now, in this case, as it is subjected to torque, it is under torsional shear stress. It is under torsional shear stress. So, let us find out the minimum shear stress okay. So, tau minimum equal to, so it is what 16T divided by pi d cube, okay, 16T divided by pi d cube. This will give the shear stress. Okay. Now, we substitute 16. Now, this is what a minus, because we have an minus here. Okay. 16 into 300, it is meter is there, convert it in mm. Okay. So, how much we will get approximately minus 48 into 10 to the power of 5 divided by pi d cube. Next. So, the maximum shear stress maximum shear stress tau max equal to, okay, again it is 16T divided by pi d cube, okay, 16T divided by pi d cube. So, we will get 16T divided by pi d cube. So, here you can find out tau by r equal to T by z, okay, sorry, T by j. So, now tau equal to what? T divided by Zp, okay, tau equal to, right, is right, 16T cube, okay. So, Zp is how much? It is pi d cube by 16, okay. We will get the same value, no problem. Okay. So, if you substitute here 16 into T is 900, okay. So, 900 into 10 to the power of 3 divided by pi d cube. So, just calculate how much you are going to get, okay. So, I think it is a 144 into 10 to the power of 5 divided by pi d cube, okay. Right. Now, so let us find out mean stress and amplitude stress, okay. So, let us go for mean stress or average stress. You refer design data handbook, notify equation number, it is 2.16a. Okay. So, now it is what? So, tau m equal to tau max minus tau minimum divided by 2. So, tau max is 144 into 10 to the power of 5, okay, right, 10 to the power of 5 divided by pi d cube minus, okay. So, tau minimum is minus here, minus 48 into 10 to the power of 5 divided by pi d cube. This is what? Whole divided by 2. So, you will get a one stress here, that stress is in terms of pi d cube, okay. Next, similarly calculate the amplitude stress or variable stress. So, you refer design data handbook, equation number 2.16b. So, tau A equal to tau max minus tau minimum divided by 2. Okay. So, now in this case minus of minus, it will become plus 144 into 10 to the power of 5 divided by pi d cube plus 48 into 10 to the power of 5 divided by pi d cube all divided by 2. Okay. Here we will get pi d cube. Here we get a pi d cube. So, once you got these two, so next thing is you need to find out the fatigue stress concentration factor. Next you need to find out fatigue stress concentration factor. So, to find the fatigue stress concentration factor, you refer equation number 2.12a, refer design data handbook. Okay. So, equation number 2.12a. So, equation is KTF equal to Q in my bracket KT minus 1. Okay. So, plus 1. Okay. So, Q stands for notch sensitivity, KT stands for theoretical stress concentration factor. Okay. KT equal to theoretical stress concentration factor. So, how to get this theoretical stress concentration factor? So, you refer design data handbook. So, particularly this is what an groove shaft subjected to torque. Okay. Actually, it has to be circular. Right. So, now refer design data handbook. Okay. So, figure number, I will quote figure number here. Figure number 2.22. Okay. Figure number 2.22. So, page number 41. Page number 41. Okay. So, here you have a ratio of R by D. Okay. So, here you have value of KT. Now, you are going to get a number of curves here. So, number of curves. Okay. So, now you just look at the curves. So, now these curves are capital D by small d. These curves are capital D by small d. So, now let us calculate small d here. This is equal to how much? 0.8 capital D. 0.8 capital D. So, now let us find out 0.1 divided by 0.8. Okay. I think you are going to get 0.125 is what? The value of R by D. Okay. Now, capital D by D, this is what? 1 divided by 0.8, you are going to get 1.25. I hope so. You just check it. Now, you just identify 0.125 mark, move your scale upward, then you check out the intersection arc. That is what intersection curve. Suppose this curve is 0.125. I think you won't get a 0.125. So, you will get some 0.12 curve. Okay. we slightly go above, now this curve is 0.12, slightly go above. So from here onwards you just draw a line on left hand side, okay? Draw a line left hand side, then you notify what is the value of KT. So now in this case you are going to get approximately 1.67, okay? Now I am just writing here 1.65 here. You refer design data handbook and solve properly, okay? So once you got the value of KT, so now let us find out the fatigue stress concentration factor. So KTF equal to Q is 0.95 here, okay? So KT is 1.65, okay? Sorry, KT is 1.65 minus 1, okay? So plus 1. So approximately we are going to get KTF equal to 0.9325 something. You just calculate, okay? So now this is what KTF. Next, to find the diameter of a shaft, now it is subjected to shear stress. You need to refer equation number from your data handbook. So equation number 2.21E, okay? So equation number 2.21E. Now they have given equation here KSF, okay? That is what fatigue shear stress factor. Now in this case it is an already calculated based on the concept of theoretical stress concentration factor. You just use it as it is, okay? Now this is what a sigma En, okay, plus tau mean, tau y equal to 1 by n. Now what are the parameters you know here? Tau y is given, okay? So n is given, sigma En is given. A you need to consider it as it is completely a reverse torsion. You can select value of A 0.6, okay? And B they have given, okay, 0.85. C also they have given 0.87. They have calculated KTF, it is around about 1.54, okay, 54. Now tau y, okay, so tau y is how much? Yield stress, okay, it is a 300 megapascal. 300 megapascal, and this is how much? 210 megapascal. So tau a is what in terms of pi d cube, okay, and tau m also in terms of pi d cube, okay. So equate it, you are going to get a value of d. This is what a small d. Now to get the value of capital D, okay, so d divided by, so what you got? Okay, so capital D equal to, sorry, small d equal to 0.08 d, okay. So let us go for d equal to d divided by 0.80. You are going to get the diameter of shaft, okay. So you please solve these two problems and submit it in WhatsApp group.